All right, so we're going to get started today. Someone unmute and tell me they can hear me.
We can hear you.
Okay, cool. All right, we're good to go. So a quick update. As you probably know, Mecklenburg and based on what I heard from my friends in the legislature, Durham counties are going to shelter in place, and so I don't see why Wake County won't be soon to follow. And so we're probably going to be changing how this works. The only difference for you is probably going to be that I won't have a whiteboard behind me, so I'll have to figure out some technique to actually do this properly from my laptop. What I might do is just take a whiteboard, portable whiteboard home with me, and then it won't look that different to you. So again, apologies for this. It's just a dumpster fire with gas being poured on it. So any questions before I start today? All right, so we are going to talk about B-trees. And so there are basically two methods that we use for on-disk searching. One is B-trees and variants of B-trees, and the other is extendable hashing. Okay, so unlike sorting where merge sort and variations of merge sort were basically the only deal, there are actually two very clever and very effective methods for doing on-disk searching. Okay, and so B-trees is the first one. This was proposed by two people, Rudolf Baer I don't think he's an aspirin guy, but maybe, and Ed McCrae. I'll actually ask you, do you happen to know where these people worked when they did this? It's interesting. Probably not what you think. Like you think AT&T Bell Labs, IBM, somewhere like that. No, they actually worked at the Boeing Corporation. Oops, spelled it wrong. Disrespected them, my bad. Boeing Corp. The airplane company in 1972. So one of the most relevant and best known data structures came from a couple of guys working at Boeing. And it's interesting, I don't actually know what they were working on that caused them to develop this technique, but they did. And so a couple of you asked me, or one of you asked me last class, what does the B stand for in B-trees? And there's a lot of interesting argument about what that means. One group believes it stands for Baer, so they're Baer trees. One group believes it stands for Boeing, so they're Boeing trees. One group believes it stands for nothing. They're just B trees. And we don't really know. I guess Baer and McCrae never said what they actually stood for. So they can stand for whatever you want them to stand for. You can choose. Now, significant research followed in the 70s to improve the initial B-tree algorithm. So as I said, the algorithm is incredibly elegant, and it's one of those algorithms where you're like, man, why didn't I think of that? And so it was not hard to understand, and so it was not hard for some of the luminaries in the database and data structure communities to look at this, really appreciate it, and then immediately put forth their efforts to improve it, to make it more efficient. So people like, what's his name? It'll come to me, but different people worked on this and made some very nice improvements, which we're going to talk about actually in our discussion. Okay. So in the 1980s, B-trees were applied to DBMS, database management systems, relational database management systems at this point in time, with an emphasis on consistent B-tree access patterns. An emphasis on consistent B-tree access patterns. The reason they care about this is to ensure concurrency and data recovery. And we'll go into this more when we actually talk about B-trees, not B-trees, sorry, database management systems, RDBMS. Versus some of the newer systems like Neo4j, which is a graph database, or MongoDB, which is people would call it a document database, but it's actually what's called a non-structured database. There are some great advantages to those techniques for the particular domains they're designed for, but one of the things about RDBMS is they've been around for a long time, and they are rock solid. And so they have concurrency, they have data recovery, they have guarantees on transactional consistency, they have guarantees on the ability to actually recreate the database if some catastrophic failure occurs in any way. And so it turns out that if you're actually running a company where you can't really afford for your database to go wacko, you're much more likely to want to go with an RDBMS if you can do that. I'm not saying that Mongo, Neo4j, Cassandra, Presto, any of these other databases have bad performance or are known to be buggy, but they're certainly not tested to the level, to the sort of time frame that these other databases are tested. And so even though everybody wants to go with the new shiny, RDBMS is still a very good choice. And the current RDBMS are incredibly well designed, and they've also been upgraded to do cloud-based storage and retrieval and other things like that. So they're actually not limited to main memory. They can handle large data, and they can handle it very well. Okay. I always feel like they get a bad rap, you know. It's like machine learning, right? Oh, the deep learning, everybody's going to do deep learning. Nobody cares about anything else. Come on, man. Decision trees, SVM, naive Bayes, all of those other things, they still work really well. And they're better than deep learning in certain situations. So actually, Tianfu Wu, Dr. Wu, who works over in EC, and I were talking. And he was very excited about this new technique called XGBoost that was being shown to outperform deep learning in certain applications. And I thought it was funny because XGBoost is one of our go-to machine learning algorithms. So it was new to him, but it was, of course, well known to me. Whereas deep learning is his speciality. And I always go to him when I need information about it. But for him, it's old hat. So interesting. Anyway, getting off topic again. So more recently, B-trees have been applied to disk management, which is very interesting. So they've been repurposed for disk management purposes. So they support here efficient I/O and versioning. So many modern disk operating systems will actually support versioning. That is, when you make a change to a file, what they do is they keep the original file and they simply add the change operations as an extension to that file so that you can back up and actually get the file back at any particular version that it existed at. And they have very efficient ways to do this. And so one example would be ZFS. So ZFS is built on an efficient B-tree implementation. An efficient B-tree implementation. So these particular data structures, or this ability to do effective search over very large data stores, has found its way into areas outside of database, which is interesting. ZFS we'll talk about. ZFS is a very nice file operating system that was developed by Sun Microsystems back before they were bought by Oracle. Interestingly, ZFS is not really being used as a mainline operating file system. Apple thought very hard about using ZFS as a replacement for HFS+, and they even had a implementation that you could use if you wanted to as part of their developer program, but they decided that they just didn't feel comfortable with it. And so they've just recently introduced their new file system, which is not based on ZFS. So the original B-tree algorithm was designed to support efficient access and maintenance of an index too large to fit in main memory. So there are three basic goals for B-trees. And you have to remember that back in 1972, main memory was quite a bit smaller than it is nowadays. We're probably talking about megabytes at the most, if you're talking about a mainframe system, which is what Boeing would have available. Now you have gigabytes or terabytes of memory. But interestingly, the size of the data sets that we're managing have grown even faster. And so that makes these algorithms even more important. My initial computing environment had 48 kilobytes of memory, and you learn to be a very efficient programmer when you only have 48 kilobytes of memory, and you're using a fairly memory inefficient programming language. So my first programming language was BASIC, beginner's all-purpose symbolic instruction code. So I actually just got a request from my boss to send him a list of all the computer languages I know. So I'm busy putting together this list, and it's ridiculously massive. A lot of the languages, of course, I probably couldn't go back and do without some recollection. But things like APL, Pascal, Modula 2, COBOL, Fortran, assembler for various different CPUs, and then all the modern languages like C, C++, C#, Objective-C, PHP, JavaScript, Java. SQL is even considered a language. It's one of the top 4 data science languages. SQL, SAS, R, and Python are the top 4 data science languages. So, all right. So, what are the goals? Goal number 1 is we want to increase the tree's node size to minimize seeks. And maximize the amount of data transferred on each read. So that makes sense. And we talked a bit about that when we talked about page VSTs. So we need some way of making the nodes as big as possible to make it efficient to read and and to get as much data as we can per seek. So you might want to make them the size of a sector. You might want to make them the size of a cylinder. The internals of the algorithm will decide that. Second point, we want to reduce search times to a very few seeks. Even for large collections. So you might think that point 1 incorporates that, but you have to remember that we're going to increase the node size, but point 2 means that we have to use a reasonable amount of that node. So I could increase the node size and then just put one element in every node, and then I wouldn't be reducing search times because the tree would still be really tall because there wouldn't be very much information stored in each node. I wouldn't be taking advantage of goal 1. So goal 2 guarantees that we take advantage of goal 1. And then number 3 is that we have to support efficient insertion, search, and deletion. Local insertion, search, and deletion. And so that's that standard idea that it's not enough just to allow for efficient search. If there's not efficient ways to actually create the initial collection and keep the collection up to date dynamically, then the algorithm is not practically useful. Okay. So here's the key insight. Have you guessed what it is? It's too late because they already published this paper. But anyway, the key insight of B-trees is the tree should be built damn it, bottom up. And not top down. Okay, so you remember, and I alluded to this when we talked about page VSTs. The problem is if you build bottom down, those first choices that you make about what you put at the root really dictate the shape of the tree. Even with rotations, you can help with that, but it's hard to fix that completely. And then rotations are very expensive if you're actually doing them across pages on a disk. Okay. So Bear and McCrae said, well, let's not do that bottom top up. Let's do it bottom down. Let's start with what we assume is a leaf, and we'll fill up the leaf. And then when the leaf is full, we'll have to promote a node up to be the root of that leaf and split that leaf into a couple of pieces. But because we know what's filling up the leaf, we can pick the exact middle value. So we can get a very perfect split between the left and right subtrees. And then we can continue doing that. And so we'll continue filling up those now half full leaves. And then when one of them is full, we can again make a very smart decision about how to split that full leaf. And that will continue until we've got all the leaves full, and then we promote up and the root becomes full. But at that point, we know the root's value, so we can make a very intelligent decision about what to pick to split the root, and so on. All right? So the intuition behind this is very simple and very elegant. And that's why I said, from my perspective anyway, this is an idea where I think, wow, why didn't I think of that? It makes perfect sense, right? And that's how B-trees work. And basically that little sort of soliloquy that I gave you really is how a B-tree in its basic form works. And now all we need to do is talk about the nuts and bolts of how you do that, okay? So we begin by inserting into a single leaf, which is also the root, all right? When the leaf overflows, we split into approximately two approximately half full leaves. They're not exactly half full because one node has one value has to go up to the root. Two approximately half full leaves and promote the median key upwards to form a new root node. Critically, we defer promotion until the leaf overflows. So we can pick a key that does the best job of partitioning the leaf. And this split promote operation continues throughout the life of the B tree. What I'm describing here is basically the insertion algorithm for the B tree. This is how you build it. Okay. Any questions about this before I continue? Okay. I don't even know how many of you are there. I could be talking to myself. Oh no, it's 15 of you. Wow. Thank you. So a B tree is a generalization of a BST. A BST is just a very special kind of constrained B tree. Okay. Rather than holding one key and two subtree pointers, we hold up to k minus 1 keys and k subtree pointers. Remember, we want this node to be as wide as possible, okay? This is called an order k beta field. And that's what you need to remember is if I tell you we have an order 5 B tree, that means every node holds 4 values, 4 keys and 5 subtree pointers. Okay? So using this terminology, a BST is an order 2 B tree. And that's the smallest order you can have. So it has 1 value and 2 subchild pointers. Okay? Because k equals 2 here. So let's use an order 4 B tree to hold the same alphabet characters we inserted into the B tree, the BST, last class. Okay, and I guess I can rewrite them just so you remember what they are. C, S, D, T, A, M, P, I, B, W, N, G, U, R, K, E, H, O, L, J, Y, Q, Z, F, X, V. Okay, if I'm feeling like really lucky, we can try to actually insert these. So it's an order 4B tree. So K is 4. That means there's going to be 3 values in every node and 4 subtree pointers. Okay? So I will tell you also that inside a node, the values are always maintained in sorted ascending order. All right? So let's start and see if I can actually get this damn thing to work. If not, I'll just write out the answers. Shit. Okay. Here we go. So we would start off by inserting. I might have to move things around, but I'm going to start here. C, D, S. Those are the first values, right? In order, and then we insert T. Okay. And we have to promote now the median value up as a new root. And I have 2 choices for median because there's an even number of values here. I could use D or I could use S. And based on what I'm looking at in my notes, I'm pretty sure that I'm going to use the left median as opposed to the right median. Okay. So D would promote, and then you can see you get 2 subtrees, right? Everything smaller than D is on the left. Everything bigger than D is on the right. So the BST property, the binary search tree property, still holds. It's just that it's not a binary tree anymore. It's, in this case, an order 4 tree. Okay? So then we insert A. A goes here. Then we insert M. M goes here. Then we insert P. P would go here. And did I really? So again, we would promote M up. I'm thinking this is weird, but we're going to see what happens. It doesn't matter. Okay. So now we promote M up. Okay. And so now we've got this tree. Okay. So everything smaller than D is here, A and C. Everything between D and M is here, P. Everything greater than M is over here, S and T. Okay, so where are we at? We have a P. So now we insert I. What did I do here? Oh, so my bad. Let me go back and show you this. I had them. I didn't have my alphabet right. So over here we have S and T. And then we inserted A, M, and P. Okay. M, P, S, T. Yeah, so P should promote. Okay. M comes before P, my bad. I'm already screwing this up. All right, whatever. Okay, so we're here. I comes here. I, J, K, L, M. B would come here. All right. W would come here. N would come here. And P. G would come here. G, H, I. Okay? So now we're going to have to promote up again. So we're going to promote I up. So we're going to have DIP. And we're going to have everything less than D, everything between D and I, everything between I and P, and everything bigger than P. Okay? And let me rewrite this just so it's a little bit more. Okay, so it's exactly the same tree, just rewritten so it's a little bit better spaced out. And we got up to G, so now we're going to insert U, so T-U-W. Okay, so now we're going to have to promote T up. All right, and so we get this, but problem. This is overflowed now, so we're going to have to promote from here I. So we would get I, and then we would get D, and then we would get A, B, C, and we would get over here, PT, G, MN, S, and then UV. And I have to erase some stuff here to get these in here. Okay, and so what you should see is that the tree is growing in a very balanced fashion, right? As we're promoting up, things are maintaining their balance. We're not getting any weirdo branches that are much longer than the others. And so where did we get up to here? We did U, right? So R, K, E, E, H, H, O, I, O, P, and O. So now we've got to promote up M to this point. Okay. L, 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 M, and then space again. Let me rewrite this again so we've got some more space. So we've got I, D, M, P, T, and then we've got ABC, we've got EFG, and then over here we have KL, M, NO, P, RS, T, UV. Okay? So that's our current tree. We just inserted J.
So that's UW actually.
Say that again?
The child of T, UW.
Yep, good.
No V, just
Nope.
UW.
Where was W?
It looks like B is the very last one to add.
Yeah.
Oh, B is the very last one to add, you're right. So this is W?
Yeah.
Okay, my bad. Yep, okay. So we just added J. Yes, no, no. We added L. J, I, J, 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 K, L. Okay. Y. Okay. Q. Q, M, P, Q, R, S. Okay. Z. It's going to go here. We're going to have to promote up a W. And then here we're going to have to promote up a P. Okay. And then F. F is going to push E up. Why do we have F when I already have F? What did I mess up here? What am I missing? C, S, D, T, A. Let's just pretend there's no F, or F comes, yeah. I don't know where the hell that went, but anyway, it won't matter. You'll still see how this works. So an X, and then a V would go here. Okay? So that would be the B tree that formed from an order 4 B tree for this particular element. And if I had one extra value in there, what would happen is we would actually push up to another value. Okay, but this is fine. And so you can see that this particular tree is obviously a lot more balanced and a lot shorter than what you would get from your average B tree, BST, order 2 B tree, okay? And so that's the advantage that you get from these. And so, let me talk about some of the things that you actually are guaranteed to get when you build a B tree. So I'll just mention here that although our example is small, k equals 4, a B tree will normally hold hundreds or thousands of keys per node. Okay, and I just want to emphasize this is the index. You remember that way back when we talked about this, the index is the set of, in theory, fixed length keys that have associated with them seek locations for the main data file. So you ask for something or you store something, and it determines where in the main data file it goes, and then it puts the key in the associated location of that data in the index. So we're only talking about the index here, and that's why we can store hundreds of thousands of keys per node, because we really only have one key value plus an associated offset per entry in the binary, in the B tree, okay? So consider an order k equals 1001 B tree. Okay, so we have 1,000 values in every, up to 1,000 values in every node, and 1,001 child pointers. So if the tree was completely full, how many values could we store? Well, we have, I'll call it h equals 0, so we have the root value, which is one node, 1,000 keys, right? Underneath here, we have 1,001 child nodes. And so at level h equals 1, we have these nodes. So we have now 1,001 nodes. And each one of those can hold up to 1,000 values. So 1,001 times 1,000 is 1,000,000 keys. Okay, and then you get exactly the same thing here. There's 1,001. There's 1,001. And so at level h equals 2, you have 1,002,001 nodes and 1,000,000,000, 2,000,000, 1,000 keys, or positions for keys. Okay? So, and a size of k equals 1,001 is not very big, to be honest. So what this says is that we need at most 3 seeks to find any key in a collection on the order of 1 billion keys. And that's exactly the seek to key ratio we want. Okay? So, if I can build a B tree like this, I can find any out of 1 billion keys in 3 seeks, which is obviously way, way better than log to the base 2 of 1 billion. All right, which I don't even know what it is, but it's big, bigger. Okay. So that's the goal, and the B tree could support that kind of performance. But what's the requirement for that to be true? Anyone? You're sleeping, you're like drinking, what are you doing? You're like, what, are you asking me something? Man, come on, I'm watching Netflix. So this is only gonna work if we can actually fill the nodes up to some reasonable level, right? I mean, we have space for 1 billion keys, but I'm not guaranteeing yet that we're actually using that space efficiently, right? Remember when I said if I only put 1 key in every node, this isn't gonna work? And that's true. Then we would only have 1 million keys, give or take. Okay, so it turns out that the B tree algorithm guarantees some important properties on order-k trees. Okay, and those guarantees will give us this performance. Okay. So the B tree algorithm guarantees some important properties on order K trees. To guarantee efficient search, management, and space utilization. And these are the properties. First, we already know this, but every tree node holds up to k-1 keys and k subtrees, subtree pointers. That's the definition of an order KB tree. So we already knew that. Number 2, though, this is important. Every tree node holds, except the root, at least the ceiling of k over 2 minus 1 keys. So what is this telling us? In essence, this is telling us that every node except the root node is guaranteed to be at least half full. All right? It could be more full than that, but it's not going to be any less full. And you can actually see that if you think about it intuitively. So when a leaf overflows, we split it into 2 leaves and we promote up a value. So those 2 leaves are going to be about half full, which would be ceiling k over 2 minus 1. Okay? So you can see with this split, promote, split, promote, split, promote, it's guaranteed that every node except the root node is always going to be at least half full. And since every node except the root node is going to be at least half full, that guarantees that we're going to have at minimum about 500 million keys in a tree of height 3, order 1001. So we're going to get the performance that we want. Okay? Yeah. So that's a critical guarantee. Number 3 is that all leaf nodes occur at the same level in the tree. And again, that's intuitive, right? Because we do the split, promote, split, promote, split, promote. We're building bottom up. So we always start at the bottom level, and only when that bottom level is completely full do we start promoting to the next level above it, and only when that level is completely full do we start promoting to the next level above that. And so because we build bottom up, we're guaranteed that all the leaf nodes are at the same level in the tree. So what that means is the tree is always going to be balanced. There's never going to be any really short paths and any really long paths to get to any particular key. And so it's going to take the same maximum amount of time to find any key in the tree. As we showed in our example, 3 seeks maximum for our k equals 1001 order tree. Finally, and this is just another property, all keys in a node are stored in ascending order. And so that's just something that you have to guarantee, otherwise none of these other properties, well actually the B-tree algorithm won't work if you don't do that. So, okay. Are there any questions about any of that? Basic idea of B-trees. Okay, I'm gonna stop here and let you go. The only thing I'll mention is that I'm recording these and then I do some post-processing on them. And I figured out, at least for now, how to put them up on YouTube. So if you go to the Moodle homepage, there'll be a bunch of, well, there's one, but now there'll be 2 links to YouTube videos that are basically this lecture. So if you're bored and you feel like being even more bored, you can go and check out this lecture. Or if you didn't bother coming, which is perfectly fine because you don't have to come, and you want to see the lecture later, you can just jump over there and check it out. What do they say on YouTube? Smash that subscribe, smash that like button. I don't actually care about any of that. I don't even think I'm allowed to make money off YouTube, so do whatever you want. Yeah. Comment, criticize. And again, if you have any particular comments about how you'd like these to run in a different way that's going to be more useful for you, email me, send me that, and I'll try to do what I can. All right? Any questions before I let you go? All right, thank you, and I will see you on Friday in some form or other. All right.
Thanks, Tricky.
Thank you.